Hello, my name is Charlesetta Walker, and this is my final presentation for the Crime Analysis for Predictive Policing in Baltimore City, Maryland. This presentation will cover the Data Analysis Project Description, Dataset Description, Data Analysis Strategy, Results Review, Recommendations, Lessons Learned, and the Next Steps. The purpose of this project is to reduce the crime rates in Baltimore City, Maryland. The objective is to provide the police department with effective methods to combat victim-based crime incidents by using data analysis. We will use historical data obtained from police logs, and they will be used to determine high crime frequencies, primary locations, and specific time frames at which these incidents are most likely to occur. In this project, we will attempt to use a multi-step analytical approach using descriptive, clustering, and predictive techniques. These methods will provide tools for better policing and enable the strategic deployment of resources for faster response and increasing perpetrator arrest, hopefully to deter future criminal activities. What is predictive policing? According to the National Institute of Justice, predictive policing tries to harness the power of information, geospatial technologies, and evidence-based intervention models to reduce crime and improve public safety. Hopefully, through this project, we will assist law enforcement from reacting to crimes into the realm of predicting what and where something is likely to happen and deploy the proper resources. In order to have a better understanding of this project and its goals, it is necessary to have a basic understanding of the City of Baltimore and its police department. There are approximately 2,779 officers patrolling 9 district police stations. The boundaries map shows a color-coded outline of each district, and the points on the map represent the location of the district police station. The City of Baltimore is ranked number 26 in U.S. city population, ranks number 6 for violent crimes, and number 2 for homicides. There are approximately 624,000 citizens living in 320 neighborhoods. The data file used in this project was obtained from the Open Baltimore website. This database contains incident information logs that are updated and maintained by the Baltimore Police Department. The file information contains victim-based content, including date, time, crime type, crime code, crime location, weapon used, location by street address, geographic coordinates, the district, post number, and neighborhood area name. Victim-based crimes have specific identifiable victims. So this project does not include all crime types, such as illegal firearms, drug possession, bank fraud, cyber crimes, etc. This section is a high-level review of the data used. There are 276,053 rows of individual crime records contained within a structured table. There are 12 variables, 11 class types of nominal, and 1 interval type. The time period covers from January 1st, 2011 through September 10th, 2016. There are several relationships between attributes. Crime code is a subset of the description and contains more detailed crime information. Some of the crime code values are related to weapon. The post is a further division of each district, and the neighborhood is a further division of each post. The location or address is also a further division of the neighborhood. On the left-hand side is a statistical table of each variable. It contains the variable name, the description, the class level counts, the most frequently used values within that attribute, and the percentage that the most frequently used attribute contributes to the total. Before the data file is used for analysis, several data preparation steps are necessary. Using SAS Enterprise Miner and Microsoft Excel, I assess the summary statistics, including missing values, anomalies, errors, frequency counts, and other issues. The anomalies found included the crime code definitions. Some values were obscure. The neighborhood count, the official count is 320 and only 279 are represented. The district has an official count of 9 and there are 10 represented. And the inside-outside location should be a binary class instead of containing 5 classifications. The next step was to locate any possible coding errors and apply logical corrections if they were feasible. Then I determined the missing values and applied the most viable solutions depending on the analytical method. One attribute that stood out was the weapons. There were 65% missing. It was decided the best course of action was to impute the missing values with the value of unknown. The next step was to add necessary values for processing, and that included the year, the month, the day of the week, the shift divided into 6 bins, which was taken from the military times that were recorded, the latitude and longitude for geographical mapping. Next, I renamed some of the variables for clarification, such as description was changed to crime type. And for the analysis phase, I removed any remaining rows with missing values. The values in some of these attributes were so specific that imputation was not practical, especially for locational information. The overall strategy for data analysis is to uncover associative patterns between attributes and predict crime. There are 4 main methods. Descriptive analysis is used to give an overall picture of crime incidents throughout sections of the city. Geospatial data is used to uncover the hotspots. Historical data is used to detect changes compared to other periods of time. Trends and sudden spikes can be detected this way. Next, association rules. The first considered technique was clustering, but the association rules was a better fit for this type of data. It is used to uncover possible close links between incident characteristics and the results can be used to determine the best inputs and target outcomes for the predictive stage. For predictions, we use two methods: decision trees and neural networks. Decision trees are useful in both predictive and classification tasks and consist of a set of rules to divide heterogeneous data into smaller, more homogeneous groups of data with respect to a particular target outcome. The neural networks method has generally higher accuracy for predictions, but it has a more complex structure. The weighting algorithm can produce a probability score for the target class, and filtering of independent variables allows for focus on the most problematic city sections. The analytical software tools used include Tableau for visualization and a descriptive analyzation, SAS Enterprise Miner for predictions of using decision trees and neural networks, and the R programming language used together with RStudio, which has convenient packages for associative analysis. There are two main expected outcomes for this project. First, the realignment of resources to better manage crime hotspots, and this is used to reduce patrols during times of low criminal activity and increase for times of higher criminal activity. Also to identify upward crime trends and sudden spikes, targeted investigations in order to find specific causes and perpetrators, and tailor police training for effective handling of specific crimes and the hotspots. The next outcome is crime deterrence. This is for strategic patrolling to decrease response times, increase chance of suspect capture, and also increased arrest should prevent repeat criminal incidents, and also to enhance proactive community safety efforts for both businesses and citizens. Here we have the results of the descriptive analysis, which is the first stage of the project. The graph on the left shows the frequency count of each of the crime types. Larceny, common assault, burglary, and larceny from autos are the most frequently occurring criminal activities. The top four crime types comprise nearly 70% of total incidents. This crime type information will be used to narrow the focus in the predictive analysis stage. The highlighted heat map seen on the right shows a crime breakdown by district. The northeastern and southeastern and central police districts experience the highest total crime occurrences. It reveals which districts have experienced the most of a select crime type. The Eastern District stands out in relation to a relatively high incidence of common assault. This locational information is also used to narrow focus in the predictive analysis stage. The top four crime types are used to do a further descriptive analysis. The line graphs on the left display historical data on the time frames including the month, the time of day, and the day of week. The weekend crime rates show significant incident drops for both larceny and burglary, with spiking on Mondays and Fridays. Common assault and larceny from cars increases moderately on the weekends, especially during the 2014 through 2015 period. Significant drops in February are seen, with gradual rises in the spring, summer, and fall months. The exception is common assaults, which peak around May. All incident drops during the night hours, but they peak at different times. Highest crime densities appear to be located at the central and bordering districts, as seen in the geographical mapping on the right side of the screen. In pattern detection, the mapping can be filtered for specific locations and comparisons over different time periods. Next, we have the results of the associative analysis. The histogram on the left-hand side shows a frequency count of the values input into the rules formula. This histogram chart reflects and summarizes much of the information that was discovered in the descriptive phase. Again, it can be read as the top criminal activities involve larceny, burglary, and common assault, occurring during the early and late evening, mostly on Fridays, during the months of August and September. On the right-hand side is the set of rules that were generated for this set of data. And by the way, highly correlated attributes were removed for better results. The first listed rule, these are just the top 10 that are listed, concentrates on the crime of larceny. It can be interpreted as there's an 87% confidence that the Port Covington neighborhood value is associated with larcenies within the same incident. The graph at the top right is a grouped matrix for the crime type larceny, and the sides of the circle represents the support, and the color saturation indicates the lift. And I also did an associative analysis on the remaining three crime types, the high frequency crime types of common assault, burglary, and larceny, and those larceny from autos, and those details can be seen in the written report. The next phase of the project involves the results for the predictive analysis. There were two analyses done, Model A and Model B. In both of these analyses, two methods were used, the decision tree and the neural network, and the comparisons of the results are contained in the table to the right. My initial strategy was to use the 6 shifts as the target outcome, but the results were highly unsatisfactory. So here we see Model A, and the change I made to the data included the additional attributes of the binary that contained binary values of 1 and 0. The 1 represents the total of the top 4 crime types, which is a combined grouping of larceny, common assault, burglary, and larceny from auto. This model is sampled to reflect a 50-50 balance for the target outcome. The neural networks model did not significantly lower the miscalculation score. So the decision tree, which is seen on the actually an abbreviated version of the decision tree, is seen on the right hand side. The variables of importance were limited to the shift and post attributes and the usefulness for predicting the target outcome 1. The node shading represents the deeper color saturations represent the highest percentage for the target outcome of 1 or 0. At the bottom is a shift definitions that gives the meanings of each of the shift values. The input data was partitioned into a 60% training set and a 30% validation set and a 10% testing set. We see the results in the classification chart. Both the decision tree and the neural network results are shown. The blue shading represents the correct classifications, and the red shading represents the incorrect classifications. The chart at the bottom gives a numerical totals for each of the training and validation sets. For the Model A assessment and findings, we found that the model performed with an overall accuracy rate of about 60% when classifying both outcomes. This was a fairly modest performance. There may be hidden variables that are affecting the prediction results, such as unusual weather patterns or negative events. And those negative events could include some civil unrest in Baltimore during the protestation of police violence. And there are individuals who take advantage of such events, sometimes by looting and stealing. Those are the kind of negative events that might have an effect on the predictive score. The results show that shift times to be a major predictive factor, but the post number listings may still be too broad to use for locational information. The implementation of model and measurement changes will ultimately determine if this method is viable, or or should there be a requirement to change some of the attributes, or even alter the method somewhat. Here we have Model B, the results for Model B, and it has basically the same setup as Model A, except there was a filtering of the data that only focused on the top 3 crime level districts. And we see the results using once again, the decision tree on the right hand side of the screen. The input rows were reduced to focus on the northeastern, southeastern, and central districts. Once again, it is sampled to reflect a 50-50 balance for the target outcome. And the neural network model, once again, did not significantly lower the miscalculation score. So once again, we chose to focus on the decision tree results. The variables of importance were limited to the shift, neighborhood, and year variables. as usefulness in predicting the target outcome. And once again, the color saturations represent the highest percentage rates for the target, either target outcome of 1 or 0. And here we have the results of the validation assessment for Model B. And the classification chart is a visualization of both the results for both types of model, the decision tree and the neural networks. And the table at the bottom right gives the numerical breakdown for Model B training and validation sets. The Model B assessment and findings. The model performed with an overall accuracy rate of about 61%, just a tiny bit better than Model A, when classifying both outcomes. Once again, it had a modest performance. And again, it's possible that hidden variables may be affecting the predictive results. I would recommend this model over Model A because the results show that the shift times to be the major predictive factor. However, a more narrow locational factor, which is neighborhood, provides a more precise information for assigning police resources. Filtering to one district could make this type of model more useful for patrolling target crime group hotspots. The way to measure this is to implement the model and measure any changes in the crime rate, and that will ultimately determine if this model is viable enough or some changes need to be made to increase the accuracy rate. After closely reviewing the results of the data analysis, I have several recommendations for implementation and for further research and analysis. For implementation, focus strategies on limiting and preventing incidents involving larceny, common assault, burglary, and larceny from autos, and that should make a significant impact on reducing crime rate. The next is to build a dashboard for each of the districts that reveal updated information, and it should highlight or give alerts for crime type spikes in certain neighborhoods. There should be an emphasis on the use of geographical heat maps. Visual investigative tools would be important for uncovering patrol area crime patterns, and it should be filtered or could be filtered by any number of criteria, including weekly, daily, or a portion of day historical data. And also, the information can be used for community policing. The findings can support and promote crime prevention strategies within problem areas such as a neighborhood watch, personal safety training, CCTV, a closed circuit TV, and added street lighting if required. The suggestions for further research and analysis include database improvements. A unique ID column could be added to the incident reports and other public safety data, such as arrest records, so that more pertinent data can be linked together and included in further analysis. And a code book of reference would also be very useful. And also consider incorporating other data sources such as 911 call logs, perpetrator stats, property values, poverty levels, etc. But you would also need to use discretion to avoid unwieldy or overcomplicated processing of these different data sets. And there should also be accounting for crime times and locations that would naturally spur increases in specific criminal activity, such as larceny from autos, that would commonly occur near major entertainment venues and special events, such as sporting games. Um, and also utilize other statistical analytical methods to improve the prediction accuracy. The data files can be reconfigured to include more numeric values for logistic and linear regression techniques. And also, it's important to research successful predictive policing strategies that have been utilized in other large cities. This is a constantly evolving subject that currently has some conflicting and controversial approaches. After much research on the subject and the repreparation and building of several models, there were a lot of lessons learned while performing this project. This is just the highlights for me. First, the raw data file was found to be more limited for predictive analysis than I originally assumed. Um, but I believe that the database, the Baltimore database, could benefit from several improvements, which were mentioned in the recommendation section. The data preparation required more careful consideration and planning. There were numerous alterations in my approach due to some limitations in analytical tools and methods that I used. For instance, initially all homicide incidents were inadvertently removed due to a decision to remove rows with extensive time coding anomalies. I was forced to go back to reinterpret those values. Then I was able to successfully correct each of the values, and that was quite time consuming. Next, uh, experimentation and comparison with several other analytical tools may have provided more useful results or higher accuracy. Those tools could be Watson, RapidMiner, Prediction, and others. Internal police database codebook definitions are important for this type of project. Some of the external resources provided were conflicting and had incomplete information. I do believe if this were an official partnership with the Baltimore Police Department, that would have resolved much of that issue and save some time. And also some conflicting recommendations for best approaches to crime data analysis and when it came to predicting crimes. In some other cities, there has been a lot of trial and error when shifting resources for crime reduction. Um, I know in Detroit they changed the shifts to 12-hour shifts for police officers, and they had to go back to the regular 8-hour shifts after pushback from the police unions and community leaders. And it is a predictive policing is a very controversial subject, especially due to the recent police incidents in Baltimore. this year and last year. But it was a very interesting project, and I hoped to be involved in something similar in the future. At the end of this project, the next expected steps include submission of the final project report to the project stakeholders and clarification of any details in the report if requested. Then, upon project approval, a systematic updating of the data inputs for machine learning. Next would be implementation. Build dashboards that would filter for individual district and sub areas, including heat mapping included with the dashboards. And this would result, or assumed it would result in the reassignment of police resources accordingly. And finally, the evaluation and any necessary revisions. Measure the results against the comparable timeframes and improve prediction accuracy with revised data strategies and methods. Thank you. This now concludes the final presentation of this project. If you have any questions, please feel free to contact me, Charlesetta Walker, at the contact information shown on the screen. Thank you.